Welcome to G Fun Facts Online. Have you ever looked up at the night sky and seen the full moon, usually a familiar pearly white, glowing with an eerie, deep red color? This is the astronomical spectacle known as a, quote, blood moon. For thousands of years, this celestial event has sparked wonder, fear, and myth. But what's really going on up there? Today, we're going to pull back the curtain on this cosmic magic show and reveal the fascinating science that paints the moon red. It's a story that involves a perfect cosmic alignment, the Earth's atmosphere acting as a giant lens, and the same physics that explains why our sky is blue. Let's dive into the intricate dance of the sun, Earth, and moon. To understand the blood moon, we first need to talk about what sets the stage: a total lunar eclipse. A lunar eclipse happens when the Earth positions itself directly between the sun and the moon. When this happens, our planet casts a massive shadow into space, and the moon passes right through it. This perfect alignment, where the sun, Earth, and moon form a straight line, is called syzygy. Now, Earth's shadow isn't just a simple, uniform dark spot. It's actually made of two parts. There's a fainter outer shadow called the penumbra, and a much darker central shadow called the umbra. The type of lunar eclipse we see depends on which part of this shadow the moon travels through. First, there's a penumbral lunar eclipse. This is when the moon only passes through the faint penumbral shadow. These events are often so subtle that you might not even notice the moon getting slightly dimmer unless you're paying very close attention. Then, we have a partial lunar eclipse. This is more dramatic. A portion of the moon enters the dark umbral shadow, making it look like a dark, round bite has been taken out of the lunar disk. Finally, we have the main event, a total lunar eclipse. This is when the entire moon passes completely through the Earth's dark umbral shadow. And it's during this total phase that the moon can take on that famous reddish hue, earning it the nickname blood moon. You might be wondering, if there's a full moon every month, why don't we get a total lunar eclipse every month? It's a great question, and the answer lies in the tilt of the moon's orbit. The moon's path around the Earth is tilted by about 5 degrees compared to the Earth's orbit around the sun. Because of this tilt, during most full moons, the moon passes either just above or just below Earth's shadow. The cosmic alignment has to be almost perfect for an eclipse to occur. When it does, a total lunar eclipse is visible from anywhere on the night side of Earth, as long as the skies are clear. So the moon is now completely inside the Earth's darkest shadow. Logically, you'd expect it to just disappear, to become a black circle in the sky, completely cut off from the sun's direct light. But instead, it often glows with a haunting, coppery red light. How is this possible? The answer isn't in space, but right here at home, in our own atmosphere. Imagine you could take a trip and stand on the surface of the moon during a total lunar eclipse. Looking back at Earth, you would witness something incredible. Our planet would appear as a huge, dark disk, completely blocking out the sun. But it wouldn't be just a black circle. Around the entire edge of the Earth, you would see a brilliant ring of reddish light. What you're seeing is the combined light of every single sunrise and every single sunset happening on Earth, all at the same moment. It's this ghostly ring of refracted sunlight, filtered through our atmosphere, that travels onward into the shadow and gently illuminates the eclipsed moon. Our atmosphere acts like a cosmic filter and lens. As sunlight grazes the edge of our planet, the atmosphere bends or refracts some of that light into the umbral shadow. But here's the crucial part. The atmosphere doesn't treat all colors of light equally. And to understand why, we need to talk about a fundamental principle of physics called Rayleigh scattering. Rayleigh scattering is named after the 19th century British physicist Lord Rayleigh. It describes how light scatters when it interacts with particles that are much smaller than the wavelength of the light itself. In our atmosphere, those tiny particles are primarily the molecules of nitrogen and oxygen that make up the air we breathe. We see sunlight as white, but it's actually a spectrum of colors, like a rainbow, from violet and blue on one end to orange and red on the other. These colors have different wavelengths. Blue and violet light have short wavelengths, while orange and red light have much longer wavelengths. The core rule of Rayleigh scattering is that the amount of scattering is intensely dependent on the wavelength. Specifically, it's inversely proportional to the fourth power of the wavelength. In simple terms, this means shorter wavelengths get scattered far, far more effectively than longer wavelengths. This single principle is responsible for one of the most basic facts of our daily lives. The sky is blue. As sunlight streams into our atmosphere, the short wavelength blue and violet light hits the air molecules and gets scattered in every direction. This scattered blue light comes at our eyes from all over the sky, so the whole sky appears blue. Our eyes happen to be more sensitive to blue than violet, which is why we see a blue sky, even though violet light is technically scattered even more. Now think about a sunrise or a sunset. When the sun is low on the horizon, its light has to travel through a much thicker slice of Earth's atmosphere to reach you. Along this long journey, most of the blue and green light gets scattered away from your line of sight. What's left to complete the journey to your eyes is the longer wavelength light, the reds, oranges, and yellows. This is why sunsets and sunrises are so brilliantly red and orange. So let's take this understanding and apply it back to our blood moon. As sunlight grazes the limb of the Earth, it enters our atmosphere. The two lowest layers, the troposphere, where our weather happens, and the stratosphere above it, are dense with those nitrogen and oxygen molecules. First, these layers act as a lens, bending the sunlight into the shadow cone behind Earth. As the light passes through this thick layer of air, Rayleigh scattering goes to work. The air molecules scatter the short wavelength blue and violet light away in all directions. But the longer wavelength red and orange light is less affected. It continues on its path, gets bent towards the moon, and bathes the lunar surface in a reddish glow. The Earth's atmosphere has essentially filtered out all the blue light and projected a faint, red image of the sun onto the moon. The exact color and brightness of a blood moon can change dramatically from one eclipse to another. It all depends on the state of Earth's atmosphere along that sunrise/sunset ring at the time of the eclipse. If the atmosphere along Earth's edge is very clear, more light gets through, and the eclipsed moon will look brighter and more coppery orange. However, if that part of the atmosphere is full of clouds, or more importantly, dust and volcanic ash, the eclipse will be much darker and a deeper, bloodier shade of red. These larger particles in the air can absorb more light or scatter it in ways that deepen the red hue. To help standardize observations of these variations, French astronomer André-Louis Danjon created a 5-point scale back in 1921. It's called the Danjon scale, and it classifies the brightness and color of the moon during totality. It runs from L equals 0 to L equals 4. An L value of 0 means a very dark eclipse, where the moon is almost invisible at the peak of totality. An L value of 1 is a dark, gray, or brownish eclipse, where you can barely make out details on the moon's surface. L equals 2 is a deep red or rust-colored eclipse, often with a very dark center. L equals 3 is a classic brick red eclipse, usually with a brighter yellowish rim around the edge of the shadow. And finally, an L value of 4 is a very bright copper red or orange eclipse, often with a bluish, very bright rim. What causes these different ratings? A big factor is the presence of volcanic aerosols in the stratosphere. When a major volcano erupts, it can pump enormous amounts of ash and sulfur dioxide high into the atmosphere, where it can linger for years. These particles create a much denser filter for sunlight to pass through. A famous example was after the massive eruption of Mount Pinatubo in 1991. For the next couple of years, lunar eclipses were exceptionally dark. The total lunar eclipse of December 1992 was so dark that many observers rated it as a clear L equals 0 on the Danjon scale. The moon all but vanished from sight. While Rayleigh scattering is the star of the show, it's not the only type of light scattering happening in our atmosphere. There is also Mie scattering, which happens when the particles in the air, like dust, pollen, or water droplets in clouds, are roughly the same size as the wavelength of light. Mie scattering isn't as color-dependent as Rayleigh scattering and is responsible for the white glare you see around the sun on a hazy day. It's also why clouds appear white. Then there's non-selective scattering, which occurs when particles like large water droplets in rain clouds are much larger than the light's wavelength. As the name implies, it scatters all colors of light equally, which is also why fog and thick clouds look white. During a lunar eclipse, the presence of these larger particles that cause Mie and non-selective scattering can absorb more light, contributing to a darker, less colorful eclipse. For millennia, before we understood the physics of light and orbits, the blood moon was a source of profound mystery, and often, terror. Cultures around the globe created rich mythologies to explain the moon's sudden, frightening transformation. In ancient Mesopotamia, astronomers were skilled enough to predict lunar eclipses, but they viewed them as a direct assault on their king. To protect the real monarch, they would appoint a temporary proxy king who would bear the brunt of the celestial omen, while the real king went into hiding until the danger had passed. To the ancient Incas of South America, a blood moon meant that a celestial jaguar was attacking and devouring the moon goddess. They feared that after finishing with the moon, the jaguar might descend to Earth to prey on people. So they would make as much noise as possible, shouting, shaking spears, and forcing their dogs to bark and howl to try and scare the cosmic predator away. In some Hindu folktales, a lunar eclipse is caused by the demon Rahu. As the story goes, Rahu managed to drink an elixir of immortality, but was promptly decapitated by the gods. His immortal head, seeking revenge, forever chases the sun and moon. When he catches and swallows the moon, an eclipse occurs, but since he has no body, the moon eventually re-emerges. Not all interpretations were so dire. The Bata Maliba people of Togo and Benin in Africa viewed a lunar eclipse not as an attack, but as a conflict between the sun and moon. They saw it as a time for reconciliation, encouraging people to end feuds and make peace with their enemies to help resolve the celestial conflict. Similarly, the Hupa and Luiseño tribes of California believed the moon was wounded or ill, and they would perform healing ceremonies, singing chants to restore the moon to health. These stories show just how deeply celestial events are woven into the fabric of human culture. So, if all this talk has you excited to see one for yourself, what's the best way to do it? The great news is that observing a lunar eclipse is one of the easiest and most rewarding astronomical experiences. First, and most importantly, unlike a solar eclipse, a lunar eclipse is perfectly safe to view with your naked eyes. No special filters or protective glasses are needed. Just find a spot with a clear, unobstructed view of the sky, away from tall buildings or trees. If you can, try to get away from bright city lights. While you can still see it from a city, escaping light pollution will dramatically enhance the experience, making the colors richer and the surrounding stars more visible. While you don't need any equipment, a pair of binoculars or a small telescope will give you a stunning, detailed view. You'll be able to see the Earth's curved shadow slowly creeping across the lunar craters and seas, and you'll get a much better sense of the color variations across the moon's face during totality. Be patient. A total lunar eclipse isn't a fleeting moment. It's a slow, majestic event that unfolds over several hours. You can watch the initial dimming of the penumbral phase, the first bite of the partial phase, the beautiful red of totality, and then the whole process in reverse. During totality, look closely. You might notice that the part of the moon closer to the edge of the umbral shadow is brighter and more yellowish, while the part deeper in the shadow is a darker red. Ready to mark your calendars? There are some great total lunar eclipses coming up. On September 7th and 8th, 2025, a total lunar eclipse will be visible from Europe, Africa, Asia, and Australia. On March 3rd, 2026, viewers in the Americas, along with parts of Europe and Africa, will get a show. And ringing in the new year, on December 31st, 2028, another total lunar eclipse will be visible for parts of Asia, Australia, and North America. The blood moon is a perfect illustration of the elegant connections in our universe. It's a powerful reminder that the same fundamental laws of physics that create the familiar blue of our daytime sky and the fiery reds of a sunset are also capable of producing this rare and beautiful celestial spectacle hundreds of thousands of miles away. It's not magic or an omen. It's a magnificent display of atmospheric optics, a projection of all the world's sunsets onto the face of the moon. So the next time you see the moon blush red in the night sky, you'll know you're witnessing the shadow of our own world, fringed with the light of 1,000 sunsets. Thanks for tuning in to G Fun Facts Online.